Hello everyone. First, I'm sorry for the delay, but in this recording, I'm going to show the moment distribution method. So, this method we will be using a lot, both when we use the equivalent frame method for two-way slabs, as well as for the analysis and design of continuous spans. So, last time you all remember we solved this problem that you see here by using the method of three moments. So I think you may all recollect what we do there. Uh, so basically what we do in the method of three moments is we we assume that the beam has a break at every support. Therefore, each of these beams is individually a simply supported beam. So, if we do that, then we will get a difference in the two rotations at the both the ends of the beam. And what we did is that we said that the net rotation on this side should be equal to the net rotation on the other side, or the negative of that, so that on the whole we have a continuous slope at every support. So by doing that we were able to generate additional equations for the redundant supports and then solve for the moments. Now moment distribution method is very popular because in this method we don't need to solve any simultaneous equations. So it is basically a step by step algebraic method. Let me explain first what is moment distribution method. It is, you can think of it as the analog of the three moments method. So what we do here is we we take this span for example, and we assume that each support in between is a fixed support, that is or not only in between, each and every support is a fixed support. This is what we assume. Then what we do is we will get fixed end moments. So we have these two loads acting here, we have a distributed load acting here, and we have a central load acting here. If all of these supports are really fixed supports, then we will have some fixed end moments. So fixed end moments at each of these beams. That is, the first beam will have it will bend like that, so it will have end moments like that. Similarly, the second beam will also bend like that, so it will have end moments like that. Third beam will also bend in the same way. Uh, so it will also have moments like that. So now we know that since these are not actually fixed supports and it is a continuous support, we know that for equilibrium at the support, whatever moment is acting on this side should be equal to the moment on this side, or else we do not have equilibrium. So basically in the moment distribution method, what we do is first we assume that all are fixed, then we start releasing the supports one by one. So what do we mean by releasing? Supposing I want to release this support, then I know what is the difference between these two moments. So let's say this moment is 60 kilonewton meter, and or not at the beam, let's see at the support. Let's say this moment is negative 60. I will tell you the sign convention in a moment. And let's let's say this moment is positive 90. Okay, so if now the difference in moments is negative 30 kilonewton meter. So if I want to remove this difference, then I have to apply manually a moment of positive 30 kilonewton meter and distribute it to both of these. So that means if I have plus 30, I need to apply according to the stiffnesses of these beams. Let's say I need to apply uh, positive 20 here, and then I need to apply here, let's say positive 10, suppose. Then in the total now, this negative 60, I'm sorry, what I needed to apply was negative 30. So let's say I distributed that negative 30 as a negative 20 and a negative 10. So now what happens is I have negative 60, negative 20, positive 90 and negative 10. So they all add up to 0. So now the moments are balanced. So basically in this method we assume everything to be fixed. Then at every joint we try to balance the moments to get 0. Now let's see the sign convention. This is very important. At supports, remember, for supports, clockwise moment is positive, counterclockwise moment is negative. At beams, it's the other way around. Counterclockwise is negative, clockwise is positive. Mainly you need to remember for supports to use the moment distribution method. Okay, now so let's use the method. Let's solve this problem that we use the method of 3 moments. Let's solve the same problem by using the moment distribution method. You will see that it takes fewer steps than much fewer than the method of 3 moments. Okay, let me just put a bigger picture. Okay, so how to do this? I will tell you exactly the procedure. First step is draw lines at every support. So here is my first support, draw a vertical line. Second support, draw a vertical line. Third support, draw a vertical line. Fourth support, draw a vertical line. Now draw one horizontal line here and make boxes for each support. Okay, one box for each side of each support. Okay, now what are we going to give here? In these boxes we are going to write the relative stiffness values. So let's see how to write that. So before we go there, just briefly recollect, we discussed this. When we have a simply supported beam, you remember that if you apply a moment on this side, then the rotation that you will get here theta. These moment and theta are related by moment is 3 times EI by L theta, where E is the modulus of the material of the beam, I is the moment of inertia of the beam cross section, L is the length of the beam. Okay, and on this side you will get half of this theta, so you will get theta over 2. Similarly, when you have a propped cantilever, when you apply moment M, then you will get half of this moment carried over, so that is the moment at the support. So if I apply M here, I will get M by 2 here. And of course there is no rotation because it's a cantilever, and the angle theta that I will get here, it is related to M by the relation M equals 4 EI by L theta. Okay, so there is an easy way to remember these two. Remember, this side is a roller support. It cannot exert moment, but the angle is half of this side. This side is a fixed support, then it cannot allow any rotation, but the moment is half of this moment. Okay, and you need to remember these two values. So why we are using these two? Very quickly, let's say you have something like that, and you have simply or a roller in between. Now let's say I apply an external moment here M, right? Now how is this beam going to twist? Like that, right? So out of this M, if I want to look at the support, because of the external moment M that I applied, there will be two internal moments like that, right? Those are going to balance M. So how much is balanced by this side, how much is balanced by this side? That depends on the stiffness. So this side, the stiffness will be, let's say this side I have length of L1, modulus E1 and moment of inertia I1. On this side I have L2, I have E2 and I2. So then the stiffness on this side is equal to 4 E1 I1 by L1. The stiffness on this side is 4 E2 L2 by I2. So just for example, let's say that E and I are same, and this length is half of this length. So this stiffness will be twice of this stiffness. The left hand stiffness will be twice of the right hand stiffness if we take E and I to be same and L to be half. So the moment out of the stiffness values, you can take them as 2 and 1, and the relative stiffness values you can take as 2 divided by total, that is 3, 1 divided by total, that is 3. So the relative stiffness on the left side is 2/3 and on the right side is 1/3. So therefore if I apply a moment, external moment M at this support, the left hand side beam will be taking 2/3 of that moment, and the right hand side beam will be taking 1/3 of that moment. I hope that is clear. Okay, next thing you need to understand is sign convention. So okay, the sign convention I already said. Remember, at the supports, clockwise moment is positive, counterclockwise negative. At beams it's the other way around. Okay, now let's come back. Now we know what is relative stiffness, so let's write the relative stiffness for this one. How to write that? So first here there is a pinned support, right? So there is no moment on the other side, everything is on this side, therefore give the value 1 here. similarly here, no movement on this side, whole movement on this side, give the value 1 here. Now for this one, what is the this is fixed, but this side is a pinned support, this side is fixed support. So when we are going to distribute it, the stiffness on the left side will be 3 EI by L. Remember, for when you have simply supported, the stiffness is 3 EI by L. When you have fixed, 4 EI by L. So for I'm taking now the support at B. So the beam on the left, you see, we assume fixed at B, but this side is pinned. So 3 EI by L. So let's write I'm just writing as scratch pad here. So what will it be for the left side? Left side will be 3 times EI divided by L is 4, right? 3 times EI by L. So right side 4 times EI by L is 8. So you can take, now I'm just saying, you please do it on paper at your end. Left side 3 by 4, right side 4 by 8. Now let's simplify that. So 3/4, and the right side can be written as 2/4. Okay, 4/8 is 2/4. So it is 3 on the left, 2 on the right. So it is 3 by 5, 2 by 5. So I write here 3 by 5 and 2 by 5. Okay. Now let's come similarly to this side. Now this side is still 4 EI by 8. So 4 by 8, EI cancels out. Right side is 3 EI by 6. So now on the left side I have 1/2, right side also I have 1/2. So that's what I have. Relative stiffness is 1/2 and 1/2. Okay. Now we got the relative stiffness. Now next step is to here write relative stiffness. Next step is to write the fixed end moments. So how to do that? Draw another line. Okay. Draw another line. Now let me just stop the recording here. I will continue. I just need to go for something.